Now let us look at align vertices operation. With align vertices operation, we can align vertices along an edge with a reference vertex using planes. Here, we need to specify along edge direction by selecting an edge, then we input the reference vertex. We can then select coordinate system, which can be either Cartesian or cylindrical. Then we input plane in which we want to move the vertex. This plane can also be user defined. This particular slide shows an illustration for the align vertices operation. As you can see, we select an along edge direction, we select the reference vertex, and we move the vertices required along the selected edge. Another way to move vertex is by align vertices in line. This way we can move a vertex by aligning it to a line. We need to specify the line direction and the vertex we want to move. With move vertices comes an option called set edge length, by which we can change length of edges. Within this, freeze vertex option keeps vertex in same location even after edge length is changed. This particular slide illustrates the align vertices inline operation. As you can see, we need to select two vertices to define an alignment direction. We do that by selecting this particular vertex and this particular vertex. These middle two are the vertices that we need to move or align. Now the direction is defined by these two vertices. So the middle two vertices are aligned in that particular direction as shown in the result. Within move vertices, there is an option called move face vertices, using which we can move or rotate face vertices. If we decide to move vertices, we can select face to which these vertices belong and also specify direction for movement. This direction can be given either by vector form or by two-point form, that is, start and end point. In order to rotate vertices, we can select vertices to be rotated along with center point angle of rotation and axis of rotation. Again, axis of rotation can be given by vector form or by two-point form. We will now move on to another operation, which is transforming block. Standard transform operations like translate, rotate, mirror, scale, periodic are available within this. We will look into these one by one. First is translate block. There are two ways to translate blocks, either by explicit or by vector method. In explicit method, we specify delta x, delta y and delta z to define translation in x, y, z direction. Delta are the differences between the distance. In vector method, we specify direction and magnitude of vector by selecting 2 points. If copy is kept on, multiple copies of blocks are created for each translation. Let us see next operation of rotate. For this, we input basic requirement of axis of rotation, center of rotation and angle. Again, axis can be specified by vector form or two-point form. The next is reflect option. For this, we select block along with mirror plane and the reflection point. Mirror plane can be YZ, XZ or XY or any other user specified plane. User specified is taken by normal to specified vector. That is, we define a vector and plane normal to it will be taken as the mirror plane. Next is scaling operation. By using scale, we can scale up or scale down blocks. This requires us to input scaling factors in x, y or z direction and center of transformation. This center of transformation can be origin or centroid of geometry or any other user specified point. By using copy periodic blocking option, we can prepare arrays of blocks. This can be used only when the geometry required is periodic in nature. First, we create blocking for initial sector geometry and then make periodic copies for geometry as well as blocks. We have to input number of copies required. If we keep increment part on, new copies created will be placed in new part with same name plus an increment number like part underscore 1, part underscore 2, etc. The split edge option, as highlighted in figure shown, allows us to edit block edges. Edges are by default linear before projection. Many times it is needed to split edge so as to have more control on edges. This is important in order to capture geometric curves and shape. Edges can be shaped using following split types. Spline. Spline allows you to select edge to be split and converted to a spline as shown in figure. Click on edge and drag to specify the desired shape of spline. The change will be applied when mouse button is released. Linear. Linear allows you to split selected edge into linear edges as shown in figure. Control point. Control point allows you to select a control point based on which the curve shape will be changed. Kindly note that split edge will also override automatic interpolation of edges during mesh computation. Next is the link edge option. This option allows us to set shape of edges. We need to select target edges and then edge for source of the shape. By this, we can shape desired edge from any source edge. This option is mainly used at curvatures where we can shape internal edges based on the boundary edges. We can control shape of target edge by varying a factor. A value of say 0.3 indicates that 30% of shape of the source edge is linked. Similarly, factor of say 1.3 indicates that 130% of source edge is linked. A value of 1 indicates same shape as that of the source edge. This variation can be seen from these figures. Depending on our needs, we can change this factor. Now we move on to Premesh parameters in ICM. We are going to explore in detail various options available in Premesh parameters. The following is a list of operations in Premesh functional tab as we proceed from left to right. Update sizes, scale sizes, edge params, match edges, refinement. The first is update sizes. The update sizes option allows us to update sizes in Premesh. There are different methods available to update mesh sizes as seen in figure. By enabling update all option, Mesher computes edge node spacing based on constraint equation with default, that is by geometric mesh law. You can adjust the number of nodes on each edge based on global surface mesh size or curve mesh size, and then by default each edge will follow bigeometric geometry law. This option allows us a quick approach to preview mesh without putting much effort. Once final blocking topology is done, we go to Mesh in Functional tab, then to Global Mesh Setup and specify mesh size and say Apply. Then we go on to Update Sizes and enable Update All. We can also use Keep Distribution to adjust number of nodes on each edge based on global surface of or curve mesh size. It differs from Update All method in that edge follows geometric law assigned to it and not the default geometric law. This is the keep distribution option. By enabling keep count, we can change geometry law of edges to default, that is bigeometric. This option differs from update all and keep distribution in that the distribution of nodes is not altered according to the global surface or curve mesh size. This is the keep counts option. The scale sizes option, as highlighted in figure, allows us to specify a factor by which mesh size should be globally multiplied. After clicking apply, we will be asked whether to recompute mesh. As shown in figure, mesh size is recomputed after applying a scale factor of 2. We can easily see the effect here. Next is the edge params option. This is highlighted in the figure. It is a slightly complicated option. This option allows us to modify mesh parameters in detailed manner by specifying various bunching laws and node spacing along any particular edge. Each edge has several parameters that determine spacing of mesh along edge, such as number of nodes, meshing law, initial length at beginning end of edge, expansion of mesh from beginning end of edge to interior, that is growth ratio of mesh, and maximum element length along edge. We can see all these options here in this figure and specify these according to our needs. The edge params icon expands to a window with all mesh size parameters. Once an edge has been selected, mesh parameters for that edge will be displayed. All parameter values may be modified except for edge ID and edge length, which are predefined. We can specify number of nodes along an edge. We can select different meshing laws by which node spacing is decided. We can give spacing of first node from beginning of edge, first cell height. When an edge is selected, an arrow appears along edge. Spacing 1 refers to parameter at beginning end of arrow, and spacing 2 refers to end where arrow is pointing. Ratio is growth rate from one cell height to next. Here also ratio 1 refers to parameters at beginning end of arrow, and ratio 2 refers to edge end where arrow is pointing. We can link spacing of one edge to another by link spacing. Next is linked bunching. Linked bunching option allows distribution of nodes on a selected edge similar to distribution of nodes on series of smaller parallel edges. It defines a permanent relationship called links between these edges. Let's say we need to modify node distribution on smaller edges. We do not have to specify any node distribution on larger edge. The node distribution on larger edge will automatically be updated to reflect node distribution on smaller edges. In this way, edges are linked. Mostly this option is used if there are splits that do not cross a block, but mesh distribution on both sides need to match. As shown in figure, the smaller edge length is linked to larger edge. Thus, changes made in smaller edge will be automatically reflected in larger one. The next is match edges. The match edges option allows us to match edge spacing of a reference edge to a connecting target edge. Reference edge and target edge must meet at same vertex. Matching is done around a connected node with selected methods which come in the drop-down list. All target edges selected must be connected to same node as a reference edge. Linked spacing option, if enabled, links target edge end spacing with reference edge spacing. Any changes in node distribution on the reference edge will be automatically reflected to linked target edges. The effect is usually only noticed when target edge has an end spacing larger than reference edge, or we can cross-check end spacing on both edges, that is reference and target edges. The last option in Premesh Parameters tab is Refinement. The Refinement option allows us to refine either all blocks or any single block that we want. It refines blocks by a scale factor. A value greater than 1 will result in refinement, while a value less than 1 will result in coarsening of premesh. If all option is selected, blocks will be refined in every dimension. If we choose selected option, we can specify edge which corresponds to direction in which to modify the block. A value 0 corresponds to x or I direction, 1 corresponds to y or j direction, and 2 corresponds to z or k direction. This particular slide shows illustration of refinement operation. Here you can see that refinement is done on selective block, that is edge, which causes generation of hanging nodes. Based on what we have learned so far, let us assume we are able to generate mesh in ICM. But once mesh is generated, how will we know that generated mesh is up to mark and can be exported to solver? For this, some benchmarks are provided in ICMCFD. The pre-mesh quality option is highlighted in figure. This option is used to check quality of mesh. All elements of active volume family will be included in quality check. There are different criteria available for pre-mesh quality check. If we use edit mesh and then go to display mesh quality, for same mesh quality may be different if surface elements are included for that calculation. So be careful with this. There are many quality options available in ICMCFD, but we will restrict our discussion here to only those which are commonly used, like angle, aspect ratio, determinant, equiangle skewness, quality, etc. We will now discuss them in detail one by one. The first is angle. This option checks minimum internal angle for each element. The default is from 0 to 90 degrees. 0 implies degenerated element and 90 as perfect. Generally, an angle greater than 18 degrees is recommended for hex. Next is aspect ratio. For hexahedral elements, aspect ratio is defined as size of minimum element edge divided by size of maximum element edge. These values are scaled and default range of values is 1 to 20. Aspect ratio of 1 indicates a regular element. Maximum aspect ratio of 100 to 150 is allowed in solvers. Next is determinant. This is defined as relative determinant. It is a ratio of smallest determinant of Jacobian matrix divided by largest determinant of Jacobian matrix. In this option, determinant at each corner of hexahedron is found. Now, instead of getting into all these details, as a CFD user or a CFD analyst, what we should keep in mind is that default range is from 0 to 1. Determinant value of 1 indicates a perfectly regular mesh element, and 0 indicates an element degenerate in one or more edges. Negative values indicate inverted elements. What you should focus is on the allowable value. A value greater than 0.2 is accepted by most of the commercial solvers. There are two types of determinants, a 2 by 2 by 2 or a 3 by 3 by 3, that is a 2D or 3D. The 3 by 3 by 3 is for hexahedral elements. The 3 by 3 by 3 is for hexahedral elements. This option is same as 2 by 2 by 2 stencil, but only difference is edge midpoints of blocks are added to Jacobian computation. Then we will move on to equiangle skewness. This quality parameter applies to tetra, hexa, quad and tri elements. Mathematically, it is calculated by equation given here. Instead of getting into detail in this equation, what we should keep in mind is that default range is from 0 to 1. 0 is degenerated element and 1 is perfect element. Generally, value greater than 0.15 is acceptable by most of the commercial solvers. Next is quality. The criteria quality is calculated differently for different type of mesh elements. For quad and hexa, quality is calculated as determinant, which we already discussed. For tri and tetra, quality is calculated as minimum ratio of height to base length of each side. This is normalized to 1. For pyramid, quality is calculated as determinant. For prism, quality is calculated as minimum of determinant and warpage. Warpage is normalized to factor between 0 and 1, where 90 degree is 0 and 0 degree is 1. Now we will see the block check option. The block checks option allows us to check blocks. Sometimes even after proper association of block and good quality premesh, resulting mesh is unable to read in solver. In such cases, it is recommended to check blocks. There are different methods available for checking or fixing blocks. The run check or fix checks internal data structure for inconsistencies and fixes them if possible. Fix inverted blocks fixes all inverted blocks. Inverted blocks have a negative determinant. Invert selected block method inverts only the selected blocks. It allows us to delete blocks from topology. The delete permanently option is disabled by default. If delete permanently is disabled, block will be moved to V-orphan part. The V-orphan part is essentially dormant and mesh is not computed for it. However, it does help to maintain connectivity. Blocks can be retrieved from V-orphan region using add blocks to part option. Now, if this delete permanently option is enabled, blocks will be permanently deleted. At this point, connectivity will be broken and V-orphan region will be rebuilt. This can be useful in some situations, but this will also result in the re-indexing of blocking. The resulting index structure is usually more complicated and may be more difficult to work with. We all know that after meshing the geometry, we are going to export it into solvers. Here we will see various options that are available for this. ICMCFD can write mesh file for different solvers. So once we are done with final premesh, we need to specify type of solver, whether it is an unstructured solver or a structured solver. As our discussion here is limited to CFD, we will think of, let's say, ANSYS Fluent or ANSYS CFX, which are unstructured solvers. ICMCFD generates a single mesh output file. All common nodes on block interfaces are merged, independent of number of blocks in model. You can generate unstructured mesh by either of the following ways. Go to File, then Mesh, and then Load Form Blocking. Or the second way is go to File, then Blocking, and then Save Unstructured Mesh. Alternative third way is go to Premesh Model Tree and then convert to Unstructured Mesh. Before we conclude, let us see few aspects of multi-block structured mesh. For those solvers which accept multi-block structured mesh, we can write multi-block structured mesh output by either of the following ways. Go to File, then Blocking, then Save Multi-block Mesh. Or go to Premesh Model Tree and then convert to multi-block mesh. The multi-block structured mesh output option will produce a mesh output file for every block in topology model. For example, let's say we have 55 blocks, then it will produce 55 mesh files. The number of output files can be reduced without merging the nodes at block interfaces using output block option. Thank you for viewing this particular session in our lecture series. If you have any queries, please post them on our e-learning portal.